In your textbook, I tell a story about an election I voted in back in 1990 that, at least in the county where I lived, ended up being a tie election. Now, it didn't matter because on statewide level it was a governor's race, but within the county it was a tie between the Democrat and the Republican. And the number of votes cast in our little county where I lived was 4,342. So I won't go through the whole story again. It's in your book, but here's the full calculation of how you would estimate the odds of getting a tie election with those many votes. In other words, if 4,342 people voted and everybody walked into the voting booth and flipped a coin to determine who they're going to vote for, what's the probability of getting an exact tie? Well, this is the calculation, and it's enormous. It's 4,342 times 4,341 times 4,340, all the way down the line until you get down to 2,172. So you have to multiply 2,171 numbers here, and then divide by 2 raised to 4,342. All right, so when I came up with this, back then, I was kind of new to teaching, and I immediately found out I couldn't calculate this on my calculator nor on the computer I had. And in fact, no normal computer program, spreadsheet program will calculate this for you, nor will any calculator that I'm aware of. And so I was kind of stuck. And then right after that, I started teaching college algebra course, and then logarithms. And so I did calculate this by using logarithms. And what would you do? You would look at the logarithm of this, and the logarithm of this product would be a sum of logarithms. So I programmed my calculator to add up the logarithms of all these numbers, and then I translated that and got an estimate of what that is, how big that number is, and it's very large. And then by a technique I'm going to show you in a moment, I calculated this number as well, and using logarithms and the power rule and so forth. So I was able to estimate that this is about 1 out of 81. So, if you had an election with those many people where people were just flipping a coin, one time out of 81 you would get a tie. So, just as a side note, in the year 2000 presidential election, where there was this big controversy down in Florida, my home state, where Bush had won by a couple hundred votes, but the election was being challenged. That was a very, very interesting time statistically, and using probability. That whole month-long ruckus over that election was really quite interesting. I actually calculated the odds of getting an election that closer. Bush ended up winning by about 500 and some votes, and the odds of that happening is pretty small, but not that unusual. Still, it's extremely small to get that close to election when you have millions of people voting within a couple hundred votes. But it happened. And by the way, the news media, they went back and they counted the votes about 15 different ways, using all the different ways anybody could think of, including all the ways Al Gore's team thought of. And Bush still won the election. So thank goodness, because it removes some doubt, at least in a lot of people's minds, as to what exactly happened down there. But it was very unusual, mathematically, to get that close, as you can imagine. All right, well, I'm going to calculate a large number like this. I won't do this one because I think I did that in my book. So I'm going to erase the board and we'll put one up. Here's the problem I cooked up. Let's calculate 5 to the 3,000 power raised to 5 significant digits. So when we get done, I'll talk about significant digits, what that means here. But it's going to end up being in scientific notation, and because it's such a large number. And you can try this on your calculator. It's way too big for any calculator out there. So here's how we could approach this problem. I'm going to set this number equal to x to create an equation. 5 to the 3,000 power equals to x. And because I want to end up with scientific notation uses powers of 10. So to me it would seem very reasonable to use a base 10 logarithm, the common log. So I'm going to take the logarithm of both sides. The log of this number is the log of x. All right? And then the power rule says that we can rewrite this by taking the 3,000 to the front. 3,000 log 5 equals log x. Okay, now what is 3,000 log 5? I happen to have it on my calculator. It is 2,096.91001301 equals log x. All right, now I'm going to keep all those decimals in my calculator. Actually, the calculators, this calculator and probably yours, stores a couple more places in there. So to retain all accuracy, you want to keep everything in your calculator, all the numbers, including the ones that are hidden inside the calculator. Now, to get back to x, I have to reverse the logarithm, and the reverse of the common log is power of 10. So I'm going to make both sides an exponent of 10. And on the right, 10 to the log x is simply going to be x. So x is my original number, so x really is this number right here. So I'm going to erase this, because I think I'm going to run out of room here. So let me erase these two lines. And in fact, I'm going to erase the x, because I know x is equal to 10 to the 2,096.91001301. Okay. So I'm going to erase this also, so hopefully if you're keeping notes, you've written this down, or you can pause the video and write it down. Alright, so we basically changed this exponent number to a different base, to base 10, from base 5 to base 10. And that makes it quite useful for our numbering system and scientific notation. Alright, now in my calculator, I'm going to subtract the 2,096 from what I had showing in my calculator. And yes, I did get, actually I have an 8 here, rounded. So 5 to the 3,000 power is actually 10 to the 2,096 times 10 to the 0.9100130081. So see, I pulled out another extra digit or so from inside my calculator when I did that. Now, if you look carefully here, this is almost in scientific notation. I need to calculate this decimal exponent of 10, and it'll be times 10 to this whole number power. So I use the rule of exponents that says that when I multiply these together, I have to add them. So I went in reverse and pulled these apart. So I separated the whole number part from the decimal part, and I used all the decimals my calculator would show me. And now I'm going to take this number and raise to the 10 power. Now that actually happens to be the inverse of my logarithm on the calculator. There's a 10 to the x power. So I'm going to hit 10 to the answer in my calculator, and I get 8.1285, something like that. So 5 to the 3,000 power is approximately 8.1285, and I'll cut it off there, times 10 to the 2,096 power. There we go. So 5 significant digits ended up being those 5 places. So actually it's 4 decimal places with a whole number in front, times 10 to the 2,096. So it's written in scientific notation. So there you go. That is the best estimate to 5 places of this extremely large number. So, and you pretty much can only do that with logarithms. So anyway, there you go.